Okay, here's some notes, some more notes on section 3.1. And this is also a diagram you see on page 100. And this is what we're going to call the alternate definition of a derivative. So it's pretty much the same idea. We have our secant line, our function, and the slope of the secant line, again, is the change in y over change in x. So, and we call this just as before a, and this is f of a, the vertical position. And rather than calling this a plus h, calling this distance h, we're going to just call this point x. So the coordinate here would be x f of a, that's the vertical position, and this point would be x f of x, that's its vertical position. And our distance here, instead of calling that h, our delta x, we're going to call that x minus a. In other words, if you take your x position, you subtract a, you get x minus a, and that's your delta x. Now remember, the slope of the secant line is delta y over delta x. So it's going to be delta y, which would be f of x minus f of a, that's the change in the vertical change, over x minus a, that's the horizontal change. And if we take the limit again, as delta x approaches 0, this is our secant line, as delta x gets smaller and smaller and smaller, then we're going to approach the tangent line. Now notice as delta x gets smaller and smaller, x is not approaching 0. X is approaching what? A. So this is going to be the limit. So as delta x approaches 0, x approaches a, so be aware of that. Because sometimes they'll give you a question and they'll say, is this the definitional limit? And they'll say, as x approaches 0. No, that's not it. The denominator has always got to approach 0 for it to be actually the derivative. So delta x approaches 0, this is your main idea. So in order for this denominator to approach 0, x has got to get closer and closer to a, so that x minus a is getting closer and closer to 0. All right, so be aware of that when you look at that sketch. And now we'll just talk about the formal definition. And here we go. Definition, alternate. So this is the derivative at a point. And the derivative of the function f at the point x equals a is the limit f prime of a, so this is at a point, equals the limit as x approaches a of f of x minus f of a all over x minus a, provided the limit exists again. So that's the important part, the limit must exist. Okay? And then we'll go over an example of this and how we can use this to actually derive a formula. And before we do that, I just want to remind you to take a look at page 101, and this talks about notation. So right up at the top of 101, there's a little paragraph that discusses different notation for derivatives, and it's pretty clear. Our book is pretty well written, so that makes a lot of sense. Okay, so let's take a look at an example. Let's take a look at an example of how we can use the alternate definition. And here we go. So this is what we want to do here. Sorry about that. Okay. So this would be an example. Differentiate f prime of x equals the square root of x using the alternate definition at the point x equals a. So again, we just pretty much follow our main formula. F prime of a equals the limit as x approaches a of f of x minus f of a all over x minus a. And then my function is the square root of x, so instead of writing f of x, I just write the function, which is the square root of whatever's in here, so that's going to be the square root of x minus the square root of a all over x minus a. You can always write your limit until you take it. Okay. And then if we substitute in, we get the square root of a minus the square root of a over x minus a, and that's going to be 0 over 0. So we can't take our limit yet. So we have to do something, and this is where we're going to use from our cal limit chart, rationalize. We're going to rationalize the numerator. So multiply the top and the bottom by the conjugate. X plus a, the square root of x plus a, square root of x plus a. And this is going to be like the difference of perfect squares, so this would be x minus a on top, and on the bottom we've got x minus a times the square root of x plus the square root of a. Now if we take the limit again, we're still going to get 0, 0, so we're going to have 0 over 0. Always check that. So what I'll do is simplify, and I can simplify x minus a over x minus a is 1, so this is what we have. And now I'm not going to get 0 over 0, so now I can just substitute. And And that's going to be f prime of a equals 1 over the square root of a times the square root of a. And that's 2 of those, so 1 over 2 square roots of a. Now, this is nice, and especially in this case, because what we can do is apply this formula to any x greater than 0 in the domain of f. Apply this formula to any x greater than 0 in the domain of x gives us this formula. If f of x equals the square root of x, then f prime of x equals 1 over 2 times the square root of x, as long as x is in the domain, or x is in the domain of 0 to infinity. Can't be negative, can't be 0. Okay? Now this is a formula, so, oops, sorry, let me get this up. I can't see this here, pardon me. So again, apply this formula to any x greater than 0 in the domain of f gives us the formula f of x equals the square root of x. If f of x equals the square root of x, then f prime of x equals 1 over 2 times the square root of x in our domain. Okay, so this is our formula. So this is actually something you can put on a flashcard. So if you see, find the derivative of the square root of x, it's just 1 over 2 times the square root of x. And we're going to use that formula a lot, so that's going to be on your new formula list. So write that down, make sure you remember it. Okay? And that's pretty much what the first section is about as far as our first day. We'll have some more material we'll cover the next lecture. Hope that helps.